Hi everybody, welcome back. I'm going to do something a little different with this video. I'm going to split it into two parts, part 3 and part 3A. And the reason I'm going to do that is I started going through the editing process of this week's video, and really there are two very distinct different parts to this video. Part of it deals with just finishing up the general restoration of the amplifier, which some of you may enjoy. And then the other one is very heavily involves schematics, circuit theory, and circuit tracing. The more I got into this protect circuit, the more interesting it got, and the more I got into actually looking over here on the oscilloscope at the different waveforms and correlating that to the different parts of the schematic itself to actually understand the concept of how the protect circuit works in this amplifier. As we said earlier in parts 1 and 2, the protect circuit in this is very unique compared to the traditional sense the overcurrent and disconnect a relay contact between the speakers and the amplifier. This does kind of a novel approach to that. Instead of disconnecting the actual speakers, the speakers stay connected to the midpoint of the output section of the amplifier. But what happens is you're going to find it shuts the bias off and clamps the signal, the input signal to the amplifier down, so that there is no bias or no drive in the amplifier circuit. It's pretty interesting. So what I thought I'd do is split it into two different videos. One that's a theory-based video, one that's a restoration-based video. I'm going to post them both the same day, and we're just going to call it Part 3 and Part 3A. So I hope it doesn't get too confusing, because all of these things were kind of done at different times, random times throughout the process, and I tried to separate all the video clips into the two categories and then make two videos from each of them. So hopefully that will make sense. It won't be too confusing, and I hope you all enjoy it. So as always, I wish you all peace, joy, happiness, and good health in your lives. I hope you enjoy the videos, and we'll see you again real soon. We're still going to do our output tests and everything on the amplifier. That'll be part 4. I'm going to save that for last, but I'm going to get these two videos up this week, so you have something to watch. All right, thank you. Well, hi everybody. Welcome to part 3 of our series on this Harman Kardon PM665. I'm having a good time with this project. I really am enjoying it. And I have the boards back in, as you can see, and things put back together. I just mention real quickly that I know I get a lot of questions. What capacitors did you use? I used the Nichicon KL series. That's these black ones right here that I'm pointing to. And the blue ones are the KT series, which is like this one down here. They're both 105C capacitors. KT series are just the standard audio grade capacitors by Nichicon. KL series are special low noise capacitors, and they're good to use in the audio path. The other alternative would be the FG, the fine gold series, which are also good caps. But I had all these, so that's what I'm going to use. Now, before we get into testing this, and I promised you we would test this at the beginning of part 3, we're going to have some schematic time. So, yep, you guys are going to have to put up with it. We're going to look at a schematic. Let me get it here on the bench. Oh boy, what a mess, huh? I got scopes here, scopes up there, test equipment everywhere. All right, here's my plan. We haven't tried this out. We're going to, first of all, turn it on and make sure there's no shorts, make sure my work was okay. And then I'm going to, well, turn on my signal generator, and we're going to just see what the waveforms look like. So let's start out. I'm going to have one bulb switched in down here. This one right here I have switched on. And I'm going to go to limit I'm going to plug this in, and let's turn it on and see if we have success. And it looks as if we do. All right. I'm going to let this cook for a little while and make sure there's no problems. As long as the bulb stays dim, then I'm going to go to full power. So I'm going to shut the camera off. I'll come back in a couple of minutes. Okay, everything seems to be good. So I think I'm going to take a chance, and I am going to go to full power. And everything seems to be in order. All right, let's get the whole thing in the camera. I have two scopes here. Now, the scope on the left is your speaker outputs. This is going into our dummy load. So you have left and right channel. Scope on the right, we're looking at two signal points. We're looking first channel, the top channel, we're looking right up here at the output. And then right down here, we're going to be looking at this JFET circuit to see what it's doing. So let's check this out and let's see what happens. I'm going to turn on the signal generator, and I'm going to bring the volume up. And as you can see, it's driving. And there it's starting to clip. And you can see there's the JFET clipping, and there's the output of the amp clipping, but there's the preamp not clipping. So this thing's working. There. What am I getting? 102 watts. All right. So yeah, that was 102 watts right there, and it looked pretty clean. So we know it works. We know it's driving pretty clean, at least visually on the scope. I think the thing to do now is let's take a look and see if we can measure our bias and our DC offset. Okay, we have the meters both set to the outputs of the speaker terminals, and you can see it is ugly, and it's pretty much how it was when we checked it the other day, if you recall from the previous video. So what we're going to do is we're going to adjust the DC offset, and that is done by these two inner pots. This one down here, I don't know if you could see it right there, and then the one over here. So I'm just going to get in there and adjust those, and we're going to see if we can get this to come down to normal. And I don't know which meter is connected to which channel right now, but whichever one moves will be the correct one. Okay, that's this channel. So let's move that down. That's pretty good right there, huh? And this takes time. Okay, let's do this channel now, because it'll move around a little while. Let's see. Okay, and you can see this one's creeping up the other way, and that's pretty normal. You have to let it settle. You really should leave this on for 10 or 15 minutes at least before you really mess with it too much. We're going to go just a little bit that way. And then we're going to do the same thing over here again. This is kind of what you have to do. You have to just kind of go back and forth and let it settle. We had a big adjustment to make. Normally you just make a tiny little tweak on it and then you let it settle. All right, let's go back to this one. You can skip the camera ahead or the video ahead if you like, because this does take a little bit of patience to do. Some people like to watch this sort of thing and some people don't. So I'll leave it up to you as I bang the camera and make you dizzy. You can see it'll just keep creeping like this. And the idea is you just want to keep it within, 5 or 10 millivolts. That's all. It's not that critical. Anything, under 50 millivolts even is not a problem, but I like to keep it as close to 0 as possible. And this will keep going on like this for a while, and then eventually what you'll find out is it'll just get to a null point after it warms up enough where it'll just bounce back and forth, positive, negative, and it'll just, like this one's doing. See, this one's starting to settle down already. This one's not done settling down yet. So we're going to have to play with it a little more. See how it keeps creeping up? But it's dropping back down, see? That's getting close. And what you're going to see now is once it's settled, you're going to see the bias transistor, as it warms up from the heat sink, it'll compensate and it'll drag the bias back down. Or what I should say, the balance. So it'll go back and forth, back and forth. And that's normal. That's what it's going to do. Transistors are very sensitive to changes in temperature. So as it warms the heat sink up, then it warms up that bias diode, things will move around. So the DC balances for the most part is set. And what we're going to do, and this one, it's still dropping down. I'll probably play with this one a little more yet. And once I get it perfect, then I'm going to switch us over and we're going to do the bias adjustment. All right, I'm pretty happy with that. Okay, continuing on here. The amplifier is well warmed up now. And we want to set our bias. And the way to do that is the service manual talks about there's a test point, and I'll show it here to you here in a minute. But we can also use these test points, which are the tops of the emitter resistors. So you have TP9 and TP8, you have TP10 and TP11, and then down here you have 15, 13, 12, and 7. Or 14, I'm sorry. So these 4 right here. And then you have TP6 and 7 here, and 4 and 5 here, which are kind of isolating everything. You see these big these high-value resistors, and they'll pass the voltage without passing current. But they actually want you to spot check each of these test points here to make sure that there's no big imbalance between each pair of transistors. So let's say, for instance, one of these resistors was open. These 2 transistors would then be absorbing all the current, which is a bad thing. So they have you set the bias with this test point and then verify that all 4 transistors are doing their job. 6 of one, half dozen the other. You can just check it here and adjust it, or you can check it here. It doesn't matter. Right now, I'm clipped on number 14. So I'm down here. I'm on number 14 and 15, if you look. And they want about 50 millivolts. Why 50 millivolts? Well, let's do a little bit of math as I drop the drop the calculator. Okay, let's turn this thing on. So first thing we need to know is we have two resistors and they're 0.33 ohms each. So when they're in series, we're reading the drop across those two resistors. So together they equate to about 0.66 ohms. And current equals voltage divided by resistance. So if we take the voltage that we're reading up there, which it's asking for 50 milliamps, so 0.05 divided by 0.66, they want about 75 milliamps of idling current through the transistors. And that's why they're looking for 50 millivolts across those resistors. So I have it connected, and you can see it's a little bit high right now. It's 69 millivolts. That's not bad, but it's off by a little bit. So to adjust that, we're going to adjust this potentiometer right here. Let's see if I can show it to you in the camera. I think we can see it right there. I'm going to adjust that one. And we're just going to adjust it till we're down to about 50 millivolts. And you can see, by the way, here's your 4 emitter resistor sets. So there's 2 resistors inside each one of these packages. And so there's 2 for this side and 2 for this side, and they're just sharing the same housing. They're special resistors. And they have the leads protrude up through the top of the body of the resistor to make convenient little test points. So you see we're hooked onto those. So we're just actually hooked on to those 2 resistors in series. Back here is the actual test point with the resistor, the high value resistors, the isolated test points, if you can get your meter down in there. But I don't really see a point in that. They still make you test it here. So what we're going to do is we're going to set this one, then we're going to move our probes over to these 2, and the idea is if these transistors are matched or close enough matched, we should have the same voltage on both sides. So they should be sharing the load equally. So let's look at that. Okay, get on the meter, get out of the reflection. All that good stuff, huh? Let's get it a different angle here, maybe. Here we go. How's that? And then I'm going to reach around the camera here and hopefully not bang it too much. Get the adjuster on here. And of course it slips off. Let's use this side that doesn't slip off. There we go. And we just adjust it till it says 50 millivolts. And they just want plus or minus 5 millivolts. This is not super critical, just so you understand. The main thing is they set that idling current to be above any anomalies that would be within the tolerance of those transistors that they're using. So if the transistors are a little bit mismatched, or they have a little bit different VBE, not only will the emitter resistors take up the slack, but also you've raised that bias voltage, that bias level above any anomalies of the transistors. If you have really perfectly matched transistors, you could reduce that theoretically, and you would notice no difference in low-level distortion or high-frequency distortion. And so this is always a margin of error that a manufacturer will put in there. But again, if you have really good transistors, you can turn that down and it will still work perfectly. It won't make any difference. People get really hung up on bias, but it's really not a huge deal. And even if you turn the bias up a little bit too high, all that it'll essentially do is make the amplifier idle at a higher current. It'll produce more heat and it won't really help anything. All it'll do is make the amp sit there and get hot when there's no signal being fed through it. So the idea is to get the bias so that these transistors are turned on so that they can operate in class AB, that the bias brings it up above any anomalies of the transistor, and that it's not too high that it makes the amp idle hot. I hope that makes sense. So, and you have quite a bit of latitude to do that. So 50 millivolts is a good starting point. The idea is follow the instructions. It's usually good. I've seen some amplifiers out there where they actually go a little bit crazy with it and they run it higher than it needs to be. And when you, especially when you've replaced it with really good matched output transistors, you really don't need to run the bias that high. You can turn it down and it'll idle cooler. But that all comes with when you do your tests for distortion and everything to make sure that the amp is performing and doesn't have any crossover distortion, anything like that. Anyway, enough about that. Let's look at the other pair of resistors now. I'm going to just move those two probes from the pair here to the pair over here. And let's see, in theory, it should be exactly 49 or 50 millivolts. And their spec is they want them to track within 5 millivolts of one another. If they're outside at 5 millivolts, then either you got something going on with your resistors being out of tolerance, or the transistors themselves are not very closely matched. And again, this is not the same matched that you would have on a differential pair on little small signal transistors. Big output transistors do not have to be matched to that degree. A lot of people, again, think about that, but you'll never be able to match an NPN and PNP transistor for VBE and HFE with one another. It's just, that's not the way they're manufactured. Don't even try to do it. It won't happen. They'll be different. Because of the way that these are more like current pass transistors is what they're being used for. They're not being used for gain. So it's a whole different ball game from the transistors that you use in your preamp or in the front end of your amplifier. So just to clear that up. So anyway, let's move these over. Look at that. 49.9. I mean, they're perfect. They're perfectly matched. So this side is good. I'm very happy with that. Let's move over to this side now and take a look at that. All right, just showing you how we're connected. We're now on the other channel and we're looking at the first pair. So we're looking at the emitter resistors of this pair of transistors. So these two pairs work in conjunction for this channel, and these two pairs work in conjunction for this channel, just so you all know. All right, and looking at this, it's a little bit low. This one's idling at 37. Don't worry about the negative. It just means that I have the positive and negative leads swapped around. That doesn't mean anything. We just care about the total value here. So we'll go in here and we'll move this one up to about 50 millivolts. There we go. Looks like our new modified potentiometer circuit is working pretty well. All right, so that one's sitting good. Now I'm going to move those probes over to the other pair of resistors. So we're going to go here. And yes, it is reading the minus. That's because I put the plus lead on the wrong side. But it doesn't matter. It'll read the same voltage either way. It'll just have the minus or not the minus. And you can see this one's about 4 4.2 millivolts different from the other side. So what that means is these two pairs are just ever so slightly different from one another. Or these emitter resistors are ever so slightly different resistance from one another. It's not a big deal. This is well within spec. There's no problems. But just so you see that there are some slight differences, that's the reason why you have those emitter resistors in there in the first place. Because output transistors are not perfectly matched, and they do have tiny little differences, and those little differences are being absorbed by those emitter resistors. That's what they're in there for. In a perfect world, if you had 4 perfectly matched perfect transistors, you could essentially eliminate those emitter resistors, and the amp would idle perfectly. It would give you a higher damping factor, and it would allow more current to get to the speakers. And a lot of people would say that would give you better bass response and so forth. But this is not a perfect world. Transistors are not perfectly matched, and therefore that's why we have those. And you'll see that higher end amplifiers, I've noticed this, where they do take care and try to at least somewhat match the output transistors, they will reduce the size of that emitter resistor. So it'll be, instead of 33 milliohm, 0.33 ohms, which is 330 milliohms, I'm sorry, 0.33 ohms, I've seen them as low as 0.1 ohm or 0.22 ohms. And they can get away with that because, number one, those amps may be running lower wattage, they may be lower power amplifiers, or they may have better matched transistors, the tighter specs when they manufacture it. Does that make a huge difference? Probably not. That's the reason you gang these transistors up in pairs to begin with. That's why we have 4 output transistors. You could actually make this amp with 2 output transistors if they had high enough current rating and so forth and wattage rating. But once again, those emitter resistors may have to be a little bit bigger because you're putting a bigger load on them, especially at idle. Again, all of these things, when you put them in parallel, those resistors go in parallel with one another, reducing the overall resistance and increasing your damping factor, spreading the load across multiple transistors. Does that make sense? So this amp is aligned. That's all there is to it. The process only took a couple minutes. Explaining it to you took way longer than doing it. So I hope that answers some questions. I get a lot of questions about this sort of thing, and hopefully that'll help some of you out. The last thing we're going to do for this amplifier is we're going to restore this board here. And like I said, I don't think there's any major problems. These caps here, though, are kind of problem childs. We know that. So we're going to replace those couple little ones down there. I have the bottom cover removed from the amplifier, and I'm going to pull each of these big capacitors, these 10,000 microfarads, out, and I'm going to test them thoroughly. And if they're just fine, I'm going to put them back in. Now, we can replace these, but I don't really think it's going to be necessary, and it would require modifying the board because of the strange pin pattern of these. And the new capacitors that you buy, these are still snap fit, but they have much wider pin spacing than a modern capacitor. The modern ones, the pins are much closer together. Sometimes you can re-drill the circuit board and modify it, but the way these ones are designed, you can see that you can't drill in between here because of the way these are spaced out. So what I think I'm going to do is test these. If they're good, we're going to put them back in because I think these will last a very long time and they're not super old. And if they're bad, then we will have to resort to making an adapter to fit the new capacitors in there. But I think we're going to be okay. All right, 1 down, 3 to go. And you know what I think I'm going to do? I'm going to just flow a little bit of fresh solder on here to make it a little bit easier to remove. And just heat them up. That'll make it easier to get this off of here. There we go. All right. I don't know what the heck's in that clothes dryer, but it's sure banging around in there, isn't it? All right, let's see if we got it loosened up. Oh yeah, we do. It has glue on the bottom too, but not a whole lot. See, just a tiny little amount. Isn't this fun to watch? So we're going to do this again. There we go. Some of this old solder gets kind of difficult to get it to flow enough to remove it. So if you add some fresh to it like this, especially if it's flux core, that'll make it a lot easier. And then you can get on there and really clean this off. And I keep bumping the camera. There we go. Trying to reach around both sides here. Whoop. All right. Now, I think on this, I was going to possibly make this the last video, but I think because I showed so many things in detail, I'm just going to do this last part of this restoration. And then I'm going to post this video, and I think we're going to do a whole video on testing the amplifier. I think you all might enjoy that a little bit better because that can be its own separate video that you can refer to later. And I'll try to do some different kinds of tests. And again, it isn't really about you have to do these tests or these are the best tests to do. I'm just going to show you a few different things that you can check, a few different methods, and hopefully some of those things will work for you, and we can learn some new techniques maybe. Because there's a few things I've been wanting to try anyway, just to see how it works out. Okay, we have 4 capacitors removed here. And let's get some test equipment out and check them. Okay, I have a LCR meter out here. We're going to use the DE5000 today. And let's connect our first capacitor now that we have them out. And you can see 10,000 microfarads, it's reading 9,230, which is about right. These are plus or minus 20%, if I'm correct. So they can be anywhere within plus or minus 20% of that. ESR is unmeasurable for this one, which on a really high capacitance cap like that, that's not unheard of. Your R theta is negative 78.4. In a perfect world, it would be negative 90, but you're never going to see that on an electrolytic capacitor. Dissipation factor is 0.204. And our quality factor is 4.88. And we went over that when we did the other meter that we have, what that all means. I'm just more concerned about the ESR in these big caps like this. I want to make sure they're all good. And there, that one's 10,000. Oh, it just dropped a little bit. And they're all going to be in the 9,000 range, I'm sure. The funny thing is, when you use these little low voltage testers like this, they all seem to read low with the capacitance. These ones that use a frequency and read off of that. If you use the Sencor, the LC53, it'll almost always, if this reads a little bit low, the LC53 will read it perfectly dead on. So depends on the type of the way you're testing it as to what it's going to read. So which one do you want to believe, I guess? I guess you just have to kind of learn your test equipment. And they're all going to read in that 9 to 9.1, 9100 microfarad. And we'll put a new one in here just to compare, but I guarantee you it's going to read the same as these. These are reading like a new capacitor. There you go. And just for a point of reference, let's get a brand new cap. Hold on a second. So here's a Cornell Doublier, and it is 10,000 microfarad, 63 volts, 85C. It's the same. Notice how much smaller they are now. And here's what I was talking about. You see how these pins are spaced so differently? And that causes a problem with the way that board is laid out. But anyway, let's connect this. You could see it's reading just the same. And if we go through it's the same R theta, it's similar dissipation factor, similar Q. Yes, the phone, it does ring. So anyway, you see that these caps are good, and it's just not worth me trying to modify the circuit board or to make a little adapter plate for these. Because what you can do is you can get a little piece of printed circuit board and drill it out for this, and then put 2 pins coming out, and then it would line right up. It's a little bit of work to do, but I don't think it's worth it. I think these capacitors will last another 10 or 20 years, to be honest, because these don't seem to go bad. I mean, not like some of those other ones. There are some other ones, like in some of the old Marantz gear, that they fail, they leak badly, but I've never seen one of these really do that. They're pretty good. So anyway, we're going to put them back in, but I'm not going to put them in because they're just in the way. We're going to recap the little ones up there. All right, let's have a little solder time chat while we're doing this. A lot of you seem to like that, which is cool. I actually enjoy it too. It's relaxing. I know when I watch other folks doing this, I really enjoy kind of listening to the conversation while they're working. And so maybe we'll do that. I know I got a couple comments before that a lot of you enjoy that. So one question I got was these kind of flattened nose, long nose pliers. And they were asking what model they are. So here it is. These are made by a company called Nipex or Nipex, however you want to pronounce it. And there's the part number of them if it's not totally worn off. Hopefully you can read that. And just in case you were talking about these other ones, I have 2 pairs that I use. These are a little bit heavier ones. Same thing. And there's the part number on them. So you can check those out. All right, let's get this cap out of here. This one is hiding underneath this big bridge rectifier. It's kind of a pain in the butt to get to, isn't it? So let's take that out. And it is a 47 at 50. Now here's the thing. That is positioned right under that hot heat sink for the bridge rectifier. So what I'm going to do is I am going to use a special capacitor for that. Let me go get it. Okay, I have just 4 of these left in stock. They're Nichicon. They're 47 microfarad at 50 volt, just like the old ones, but they are rated at 125 degrees C. They are really high temperature, very durable. These are automotive grade capacitors. They're designed to be put in very high temperature environments. And I've noticed that when you use these in the power supply around places like that, where you're right up against a heat sink or something, they tend to hold up much better than just a standard cap. So we'll put those in, and I'll have to order some more next time I place an order. And you can see why I left these big ones out of there, because you just can't get in there when you're doing that. So we're going to bend our leads over. I'm going to give them a little haircut like that. Oh. And then we are going to solder it in. So there we go. It's funny, no matter how I do these videos, there's always opinions. And that's all right, because we all have things we like different than others. It's not a big deal. I don't get offended by it. I know that there's some things that I like and that I don't like, just like you guys. And, you know, the ones that I don't like as much, I don't watch. And the ones that I do really like, I do watch. It's that simple. I don't get all uptight, though, either way. I just appreciate the fact that anybody's willing to take the time to share their time at the bench with me so that I can learn things too, because honestly, that's how we all learn. I mean, if you don't watch somebody and you don't have someone to show you things, it's very hard to learn sometimes. Let's pull these 2 out next. We'll do them. Where are they located? They're over here somewhere, huh? Already lost track of where they are. Here they are. They're up in here. Let's see. Yeah, they're right up against here, so we'll have to get those out. Let's see if I guess the wrong ones, huh? I don't want to hit the camera here. Okay. That didn't do such a good job, did it? That one did that. Let's warm that up a little more. Okay, we got that one. Let's take a look at this one. See, do we have them both? This one here is still tight. Oh, this one, I did the wrong one. There we go. Better. Okay, let's get this out. And we'll have to, that one's marked correctly. So you can see they have a minus and a plus because these are polarized electrolytics. And if you look in here, I don't know if I can catch it in the camera or not, you can see on the hole, there's one has the shading on it and the other one does not. So the shaded part indicates the minus. And so far, every one of them has been screened correctly. So you can see same thing here. So this one, the minus was pointing up, and it's up. So we need, this one needs to be 47 at 16 and 100 at 16. Let's go find a couple of those. All right, where were we? Had to step away for a little bit. So we have the 100 and the 47 back in there, the new ones, and those are KT series, 105 degree, so those should be good. All right. Let's get those ones put in. I'll just move these out a little bit. Give them their haircut. All right. And solder it up. The bigger the blob, the better the job, huh? Had a guy at work that used to say that. It was funny. All right. Looks good. I don't think there's a whole lot more to replace in there. Let's flip this back around and see. So we have one here, and we have one up there that needs replaced. I think those are the only two left. So let's get that one out up there. Let's see. That's better. Nice. Okay, so we got that one. And the other one is located where? Clean the tip. Boy, they really fold those things over, don't they? Okay. Good enough. Let's pop those out. We'll do one at a time. Let's do this one. The negative goes to the right, and the little mark is to the right, so that's good. And we need 4.7 at 50 volts, so let's grab one of those. And I found one of these 125 degree ones. What the heck, we might as well use it. It's right up against that heatsink again. That's why I like those. They're good for power supplies, but they're also very good when they're going to be somewhere that's really has a lot of temperature in it. Okay, so there's that one. I'm going to see if we can remove this one now. Is it possible that this is the one we need to remove? I removed the wrong one, didn't I? Alright. Well, I wonder how much of this I'm going to leave in the video. Maybe I'll leave the whole thing in there. I don't know. Just to really tick people off because it's so monotonous. Hey, this is my video. I'm having fun. You know, you're not the only one that's entertained by this. Oh, look at that. Now it fell underneath. Ah, lost it. Ah, pachinko. Alright. 33 at 10 volts. Nice. Okay, I don't have one of those fancy schmancy ones in 33 microfarad, but I do have a KT series, which is a 105 cap, and it's on a really nice small case. So it should be tucked up under there out of the way. Heat rises, so I think we'll be all right. Okay, let's turn this around. We'll resolder the ones that the wrong one that I did. Let's see, I'll fold that one down that way. Give them their haircut. All right. And we'll get these in there. I think we'll be good to go. Well, that looks like bubble gum right there, doesn't it? There, much better. Okay. All right. I think I got everything in camera here. Yeah. Okay, let's put these back in. And this project is done. We're ready to do our tests. Well, it's all back together. And I just need to do a little more cleaning. I need to put the speaker select shaft in there and just tidy a few things up, and this will be ready to assemble and go through all of its tests. So I'm going to end this video finally, and we'll see when we edit it how much I'll leave in. I don't know. But anyway, I think this is going to be surprising how well it performs. I'll be really happy to see how the phono stage comes out. We're really going to test that out. And yeah, I think we're ready to go. So, as always, I wish you all peace, joy, happiness, and good health in your lives. We'll be back again real soon with the next part. And until then, stay well. We'll see you soon. Bye-bye.